So, good morning. Today I'm going to talk about shapes. So now we're actually going towards some kind of structures in the images, which is new. Until now we haven't been really talking about structures, only pixels or groups of pixels. But now we want to know a little bit more what kind of structures do we have, how can we describe them, and often we want to know things like how big an object is, or telling a little bit how it's shaped. Could be that it's round, ellipsoid, square, etc. And not so much today, but we could also want to look at different sizes, comparing sizes between, say, treatments or something, and also how we can compare different images based on these shapes. Further on, we could also think about maybe putting these objects into a finite element simulation, and well, why not doing pretty renderings? And today, a little bit motivation again, how to characterize objects, computing volumes, center and extents of the object, also looking into anisotropy of these objects. So we have this well-known workflow. We do the scanning, get, say, 56 gigabytes per sample. Then when we do the filtering, it's still 56 gigabyte, or yet another 56 gigabyte, but it's less noisy than the previous couple of weeks. We looked into segmentation. Then it could land into just 1 bit per pixel, so that would reduce the data quite a lot, maybe down to less than 2 gigabytes, but 2 gigabytes is still quite a lot of data. But we only have bits or pixels, so we haven't quantified anything yet. And the first step into going to the quantification is to define what we want, and what we want for an image are single numbers or tables of few numbers to tell volume fractions, cell counts, maybe also cell stretch, or variations in the volume. And in general, the typical task that we are up to is more or less summarized by these pictograms: finding hidden objects, measuring the size of things, counting objects, also looking maybe at some mixing ratios and tracking changes. If you have several images in a row, you can maybe want to see changes in volume over time or something like that. The metrics we want to look at that can be easily extracted from the images are surface area. We can count objects. We can also look at the shape tensor. Could do principal component analysis, and a lot of more different metrics that we could look at that are computable. That they're computable doesn't really mean that they really relate to what you want to know, so you can use them as a proxy for some question that you have. There is, of course, a lot of literature on this, and yeah, the classic one is the John Ross morphometry with R. Now we are not using the programming language R, but this book has a very good overview of all these metrics, and in principle you can use the same metrics also in Scikit-Image or OpenCV. And then principal component analysis, that one is with another language, S. But also again, in that one, they tell pretty well about the principal component analysis, and well, then there is a bunch of other books and papers about shape tensors if you want to look deeper into it. The typical list of packages that we can load. In principle, the important things are from the Scikit-Image morphology. Then we have the label, region props. They are the, oh, I've labeled twice, to be sure, probably. No, but that was a typo, I believe. Anyway, these are the important parts in this one. We also, down here, have the principal component analysis in scikit-learn, and the k-neighbors, the classifier which we had last week, is also coming back again. So the first step, we have our black and white images, and the first step to do many analyses is to identify the objects in the image. And for that, we have the component labeling. And the basic task of it is in principle to put a label on all pixels that are adjacent, connecting each other, and group them into each label. This works pretty well if you have well separated objects, but if the items are touching, then you actually count two pieces as one. But anyway, this is the first step. It's usually a good starting point when you want to label things. Next week, I'm going to show a different method for doing the labeling, which is a little bit more work, but can also be handling this case of touching objects. What we do, let's just look at a test image where we have some small blocks in the image. So it's a bi-level image with 3 blocks in it. If we call this label function, we get 1 color per item or number per item, and this is what we want to achieve. And there we got it. Here we have an image of probably a traffic camera or something. And you can see some cars here. Over here, they're quite obvious, but behind the trees at the building, there are also some cars parked. And the segmentation, you can see that the cars are not really looking like cars, because there is the traffic sign that cuts this one off. This one is full. This one is cut by a couple of times. This one even more. So the cars are not really as complete objects, but it doesn't matter for this task right now. Looking at this label function, so actually every function in Python, you can always call for help, and then you get a long list. The important thing that you can actually ask for is which connectivity you want to do. If you want to do 1 connectivity or 2 connectivity, and this corresponds to the 4 and 8 neighborhoods that I have been talking about before. And that has an effect on how you label the image afterwards. And this one, actually, I'd never used. I don't really know how it's supposed to be. It looks like some kind of forward-looking connection. So let's run the labeling on this cityscape picture. And what comes out is 1 label for the background, a big label, and then each car, at least the first 2 cars, they get 1 class each. The next car, which has a cut in the middle, gets 2 classes, and this one, I think it's standing behind trees or something. It's chopped up in 3 different pieces. So this kind of labeling doesn't really sense that this is an object that should be hanging together. That is for you to interpret later, saying that it can't be this small, so either reject or put some other effort into the analysis. And now that we got the labels, we can start computing the area of the objects, and that's a very simple operation, because you essentially just compute the number of pixels with each label. And in Python and NumPy, there is this unique function. Maybe I should zoom it a bit. So, this unique function, and what it does, it's look through all the pixels and tell you how many unique values you have in this. And then we can just go through with this little loop here and sum up all pixels that have each label. In this case, I used the data frame, and then we got here the labels and how large the area is of each. So this is a way to do it. A more efficient way, because this one actually looks through the image as many times as you have labels, more efficient way is to use a histogram, because with the histogram you count pixels of each gray level, and if you make the histogram the same size or same length as number of labels, then each bin in the histogram corresponds to the area. So that is just a single run, and that's much more efficient. So this is like a shortcut to computing areas in the image. So how does it work, this kind of algorithms? There are many ways of doing it, more or less efficient. This one is nice because it demonstrates visually how it works. It's not efficient, actually. But anyway, what we do is we start with our image. In this case, it's a very simplified one where we have a cross going here and the middle piece is missing. And we want to label all these 4 segments in the image. The first step of this algorithm is to put a number on each pixel in the image, which has a 1. So here the first one is 1, and this one on this corner is 9. So in principle it's just taking the pixel index throughout the image. And yeah, you see here they end up in pretty large numbers. So the last one here is actually 81. It doesn't matter, actually. You just want unique labels. You don't. So if you could want to have also in a continuous row of numbers, but it doesn't matter. You just want an ID. So what is going on now in this so-called brushfire algorithm is to propagate the local maximum value until stability. And so you go for each point that belongs to the foreground, and for each point in this neighborhood, it could then be either 4 connected or 8 connected to begin with. And for each one of these, we look for the maximum in the neighborhood and repeat until no labels change. This local maximum is actually the gray level dilation, so we can use that in our algorithm instead of doing this loop all the time. The algorithm, if you want to look into the details, looks something like this. And what is happening is, in principle, first looking for all the numbers, doing the morphology dilation with some footprint size, and then append the values into your list. And that is essentially what is going on. And if we look at how the algorithm propagates, we have the initial image that we already saw. And in the first iteration, you can see that the maximum value propagates up. So in the neighborhood of this 1, 11 is the maximum value, so it lands here. More interesting is also looking at this part here. There you have 31, and that one propagates up and turns this one into 31. So we are starting to grow at least a little bit larger objects than we had before. Also the same here. So it's always coming from the maximum, so it's coming from below all the time with this initialization. And next iteration, we can see that the 31 is taking over this segment, 33 is taking over this segment, 81 this, 73 this. And in the third iteration, we have actually our labels. So the labels we get are 31, 33, 73, and 81. So these are the labels that we have. If you now would like to have labels 1, 2, 3, 4, then you would have to do a bookkeeping task afterwards, but usually it's not necessary. So, some comments on this algorithm. It seems to converge pretty easy. In this example, it converged within 4 iterations. Could be longer, could be less, depending on the size of the object, but this is about this. Larger images or more complicated could have thousands of components, and that would of course also take longer. But in general, there exist much more efficient algorithms, and you can find those in these publications. Again, just to comment, this book I think is fantastic, describing the morphological image processing. So if you have the interest to that, really take a look at that book. I think it's actually downloadable from Springer Link, so that's pretty easy. Wikipedia also has a nice description on it. So let's go. So the previous image was just 10 by 10 pixels, not very big. Now let's go a little bit bigger and taking one of the cars. And in this we have two objects, and we do the same kind of initialization as we did before. And this time we're going to try a little bit with the different neighborhoods. But the first iteration we got is, let's run this brush fire. We see that we did it in 8 iterations, or 7 iterations if you don't count the first one. And you can see how many groups you have in the beginning, and then it decreases into 2 groups, which is what we actually would expect. And the number of changes also rapidly decreases. So that means our blocks, they are getting larger and larger. So let's look at this one. Let's see, it should be working to run it. Yeah. And now we can see how this brush fire effect, how it's propagating through the objects. And we can see that it starts from 154 and 165. And those values, they're propagating up along the structures. And let's try 2 different neighborhoods. We can look at the current one was of an 8 connected neighborhood. We can look into maybe a 5 by 5. And the effect when you run it then is that, so it's a full 5 by 5 neighborhood. So it actually looks beyond the direct neighbor into the next neighbor, beyond that. The first effect is that we actually can do the labeling within less iterations. But one interesting thing is that we end up with only one single group. And looking at what's happening in the simulation. So in the beginning, it starts doing the 154 and 165 into the groups. But at some point, you can see that the 165 actually leaks over into the second object. And the reason for that is that our 5 by 5 neighborhood actually can look beyond the gap, 1 pixel gap between the 2 groups, and then it leaks over into the second part. So this is a way how you could, in principle, handle the case when you have a little bit of broken up pieces. But you have to be careful that you don't merge objects that shouldn't be merged. So it's a balance here. If you have very sparsely distributed things that are a little bit broken, then it's fine. If you have tight clusters of different objects, then you should be careful using this one. Another kernel would be the 4-connected one. So now we are not looking at the diagonal connections. And the first effect is that we get a lot more iterations. And in the end, we actually get 3 groups instead of 2, as we expected from the first one, or actually would expect in general from this kind of object. And what is happening, we can see that in the animation. So what is happening is, the first part is we have the large object with 165. That one is doing as it did with the 8 connected neighborhood. But on the other one, here we have 154. That is a little isolated object, and then we have 140 for the rest of this item. And that is the reason that we are not looking across the diagonal in this place here. The structure element is only looking up and down and sideways, and therefore it cannot do this connection here. Color-wise, it doesn't make a big difference because they're both pretty red, so you don't really see it in the colors here. That's a little mistake in the visualization. So if we now compare these neighborhoods, what happens? We have the 4 connected neighborhood, which gives us 3 segments in 13 iterations. We have the 8 connected neighborhood within 7 iterations and got 2 segments, which is actually looking the most natural one in this case. And then we have the 5 by 5 neighborhood, which actually closes it in 5 iterations, but it only gives us 1 segment. Which kind of neighborhood you use depends on what makes sense in your evaluation. But I would tend to only use these 2. That one is a little bit more exaggeration and exotic, I would guess. There would be other methods to link these objects together. So, if we now have our items, we have a lot of numbers, labeled items. So now we want to measure something. And one is computing the area, as we did said before. But we could also look at what changes in the volume if you apply erosion and dilation. And counting cells is pretty natural because we can only count how many objects we have, but we want to tell a little bit more and maybe comparing images to each other. So how would you start? One thing is we can look at the object position, which is the center of volume. Here we have identified 2 items. We have the large one and the small one. And in principle, we have a little set here of pixels for each object. And this is what we are going to use to compute the center of volume of this object. What we do is extracting the average of each active pixel within the object, multiplying with the position in X, Y, and Z. And from that, we can compute the average, and this gives us the center of volume or center of volume or center of area, depending on if you're in 2 and 3D. And this can be done in this way. Again, also other ways. This one is done because then we get the list of coordinates and we can make a nice table. But in principle, what this code is doing is looking for all the pixels which have the label 2, and then we add that to list for X coordinate and Y coordinate, and then in the end we compute the center of X and center of Y. And in this case, from this table, we get X and Y position, which is right here, and it, I would say, makes sense for this object. Could change the code to look at the other one, and that would probably land somewhere around here. And that is pretty good because to have this information, because then you can start doing spatial correlation between shapes and areas and their position, and telling, okay, in this corner we have larger objects than we have in that corner, and that can help you to do your analysis of your images. Can also tell you if you have clusters of different objects based on this information. Then we can also compute the center of mass, which is more or less the same thing, but this time we also add the gray level of each item or each pixel within the item. And that can, if you have a flat object, it's the same as the center of volume, but if you have fluctuations within the object, then you can see that there is a shift. So let's try with this object here. We have an intensity image. You can see there is a fluctuation in this. And yeah, here is just the black and white version of it. And if we compute the two, the center of volume and center of mass, we can see that there is actually a shift. The center of volume is exactly in the middle, but due to the gray level distribution, the center of mass is shifted towards this corner. So that it depends a little bit on what you're doing. In some cases, or in most cases, it's enough to just use the center of volume. If you have, for example, you want to get the centroid of some dots in blobs in the image. I have one example in my work where we want to identify reference dots in images, and the segmentation gives us some shape, but thanks to the illumination, this real center that we want to know is a little bit shifted. So then we use the center of mass to get the deepest center point in that image. Further information we want to know is maybe perimeter length or surface area. We can look at sphericity or orientation and, well, a lot of metrics. I'm not going to tell how each metric is computed, but in scikit-image there is a very nice tool called region props that gives us a lot of information. And if we look into the help of that one, you can see that there is, so all these within these asterisks are different metrics. And you can see there is the area, which we already computed. We can look at major axis lengths, minor axis lengths, some kind of bounding box, centroid, weighted centroid, and so on. And there is really a large number of different metrics that we can look at. And for the interested, take a look at each of these and see what they can do. There is also coordinate lists telling the coordinates of all objects within the region. And if you run that on, which image was that now? Yeah, it must have been the car image again, one of the objects. Then we get a table like this, where we can look at all the details, but this is really a huge number of numbers. Some may not even be relevant to you. So the important thing is to know what each means and then extract the ones that are relevant to you. Actually, one down here is pretty relevant, is the perimeter as well. So it tells how long the edge length is. So this is a lot of information. Sometimes it's even too specific, and often it is that if you have measured something, it's not really what you want to know. So for example, you don't need to know how long a cell is in the x direction or in the y direction, because if it's a bit isotropic, if you rotate it, you get a different x length and a y length. And then it doesn't help you to tell how long it is in the x and y directions. What you want to know is the main major and minor axis, and that you can also extract actually. So in this case, let's reduce it. We can actually, with the region props, select which information we want to compute. With that, we save time, because every metric that you want to compute takes some time, and if you have many images, every micro millisecond actually cost you some time in the final evaluation. So be sure to know which properties you want to really look at. And from this we get a little much smaller table. So we got the area is 900, the parameter length is 116, and then we have a centroid, which is apparently in the middle of this, probably 50 by 50 image. Extents is another thing which is used a lot in computer vision. It's a bounding box essentially, which tells you the starting point in the image and the end point in the image in X and Y, and possibly also in Z. But that is the size of the object, of the bounding box that can enclose the whole object. And that's useful, for example, if you want to crop each little item, then it can be helpful actually, because then you can just say, these points are the ones I want to cut out, and then you can do analysis on many tiny items instead of the whole image, which could save you time in some cases. So let's look at this car item. So this is the larger blob of the two. And if we want to find the bounding box, you could do it well through this algorithm, looking first extracting all the coordinates, and then looking for the minimum and maximum, and then you get the positions of those, and that would give you your bounding box for this object. And that we can plot, and then you can see in this way. This is in principle what is done often in tracking tasks, that you only want to know where the bounding box of something is to follow it. You don't know to know exactly the shape of it, you just know where the box is to track its behavior. So for this cityscape image, we have again the label items, and if we run now this different props, we can see we got the labels, we have a centroid, we have the bounding box, and now we want to look at what can we actually extract more from this. And what we can extract would be maybe telling what color each car has. And again, let's run the whole thing, and we can see that if we plot it, we have the bounding box, we have the centroid on the different places. Well, this is a mess down here as usually. And yeah, let's see what can happen with it. We do some statistics, but to do this kind of statistics, we may not want to use the whole image. So the first pre-processing would be to erode it, shrink each car to a minimum, hoping that the central point or the central eroded point is representative for its color. And then we train a k-nearest neighbor with all the web colors that are available. And with that, we can do the connection to what color this car actually has. And so we load all the colors, and then we train the k-nearest neighbor, one nearest neighbor classifier with all the colors. So that's the color code and the color name. And then we run that to predict what color each car has. And apparently it gives us a list here. Everything is pretty gray apparently, but if you look at the picture, it is actually also. And if we look at that one, it says this one is dim gray, this one is silver, that is dark slate gray. I think it's more greenish, but and so on. So it tells everything has some kind of grayish color, even though I would say that it should be green, but maybe we should need a little bit larger patch to check against, and potentially also adding more neighbors to get a better idea of which exact color it is. So let's leave that part. Continuing looking at these objects, we can looking at anisotropy of the objects. All objects are not round, even though physicists like to reduce things to being a sphere, because that makes nice computations. In the real world, they are not. So maybe they have some kind of different shape. And what is it, in principle, the anisotropy? So that is a difference in thickness or length in different directions. And depending on how you measure, if you look at people, you can say they are tall and skinny, short and fat, or maybe perfectly round. That wouldn't be nice. But anyway, these are words to describe the shape of an object in terms of dimensions in width and height. And putting that into numbers can be tricky because you can define it in very many ways. Here are some ideas to measure the anisotropy. You can take the longest side divided by the shortest side minus 1, or longest side minus shortest divided by the shortest, longest. And yeah, well, you can do a lot of different metrics here. In principle, all these metrics are made in a way that a 0 means that it is perfectly round. If it's in 2D or in 3D, doesn't matter, but it's would be perfectly round in this case. Or actually, 2D. 3D wouldn't. It could be one dimension could be actually stretching in between. So let's define some different of these metrics that I listed. They are defined here as Python so-called lambda functions. And then we run it and see what happens on a test case where we have this shape, which starts as a circle and then becoming more and more narrow, from getting an ellipse and then going into a straight line. And then we can see how these different anisotropy metrics, how they behave. And and you can see the anisotropy 1 just peeks out of the window as soon as it's getting more and more narrow. And other ones, they are more slowly rising. And here it's actually up to you, when you do your analysis, which kind of anisotropy metric helps you, which gives you the best sensitivity for the shape variations that you can see. And so I can't say which one is the best. In one case, the anisotropy 1 is the best case. The other one, it would be the number 4. It really depends on what you really want to do, and also the shape variations. You need to have a good sensitivity in the range where you're working, because in most cases you're having some limitations on how the shape can vary. Then we can, before the break, this will be a bit tight, I believe, but anyway, we can switch on to some statistical tools. Here we are actually going to combine two fields. One is linear algebra and the other one is statistics. And that in a way that we can do something called principal component analysis, which is taking down, actually it's helping you to make clusters of the data. But this time it's clusters in a statistical sense. And we have the clusters are explained by how big the variance is in different groups. What is done is we first have a lot of data. We compute the variance or covariance or correlation matrix, which afterwards is done eigenvalue or singular value decomposition. And the singular values of that tells how important, statistically important, each component is. And the eigenvectors, that they provide an orthogonal transformation space which can spread the data in the most independent way. And here we have an example where we look at different spectra from some spectroscopy. This is just simulated, but in principle, in the instrument, we have just noise as background. We have one spectrum with some fat, gives you this peak, and some spectrum with IR, with the protein, gives you this. And you can see that the difference is mainly that you got a peak here, and this one is more narrow than this maybe. But that's just, say, speculations about the data. Already you can see that thanks to the statistical uncertainty, it's not easy to tell. And what happens if we have many measurements and want to look at that and want to tell if one cluster is more fat-like or more protein-like and simulate a lot of spectra, then what we get first is really noisy data, and it's really hard to tell, does this really belong to this or this class? If you would compare just two curves against each other, you don't see any correlation at all. So if we now run the principal component analysis on this with 5 components, it should be sufficient in this case, and plot the eigenvalues, you can see that the most information is actually in the first 2 components. The other ones, they are really low, and that means they essentially only represent the noise in the data. And if we apply this transform from the principal component analysis, we can run different, these are, this is on the data, and we can see here that it extracts different clusters. And if we try to look at the 2 components, actually these are the components themselves. So if we see that, we can see that there is a noise class. There is one that behaves like this, and the other one has 3 peaks. And if we plot them against each other, then we can see that we have 3 very distinct clusters. And that helps us later to maybe do a k-means clustering and identify that this spectrum was the protein, this spectrum was the protein, fat, and noise. So these are very nicely separated in this example. The problem you can come to is that you forget to standardize the data, because otherwise you may have really large focus on one direction, but we have seen that also before, that you need to normalize your data. And the other thing is over-interpreting low variance principal components. They may only be noise, so the question is where to set the threshold. And oops, that was the one. So if you look at these 2, it looks like they have most of the information in them. And if you start looking at this one, you would probably only see some noise, and that can be tricky to handle. So one more example in this is a real example where we look at crystal textures in metals. And what we use is Bragg edge imaging with neutrons. And thanks to the crystalline structure, we get reflections within the material depending on the lattice distances here. And then we can have constructive or destructive interference, and that gives you responses in the measured signal. And if you do a wavelength scan across the data, you can see spectrum behavior like this. This is a face-centered cubic ion, and then you get this kind of spectral response. And here is an assembly showing a little bit of different types of crystalline structures. In the experiment that we did, we had 3D printed metal pieces, and on the surfaces there was some extra treatment, and we want to see how deep this treatment is going. And looking just on the average image, we just see homogeneous material, nothing. If we look at single wavelength bin, also not seeing much. But running it through the principal component analysis, there's one, if you're interested, you can go quickly through afterwards, but I just want to show the effect that we got here now, again with 5 principal components. You can see that there is a strong emphasis on the first component. Then this one is already pretty deep, and then it goes even deeper and deeper because this is a logarithmic scale. Plotting these, you get the principal components look a bit wild, and also the 2 first components plotted against each other looks like a clutter in this way. And if you have a plot like this, a trick is actually to play with the opacity, and instead of having this completely opaque cluster, you can start seeing that you have 4 distinct regions, and those can be used then to identify regions in the material. And another way is also that you can use the first 3 principal components to color code the data. And if you look at the white beam data and PCA enhanced color coding, you can see that there is actually something going on along the surface areas in the data. And yeah, then plotting everything together. I think I have to skip this part, otherwise we will be in a very rush. In principle, what you also can do is, with the help of principal components, you can identify the principal orientations of an object, and with that you can rotate it along the minor and major axis. Minor and major axis is something you can get automatically also through region properties, and this is a way how you can compute it. And also, of course, you can rotate it if you apply the transform using the Q matrices. Yeah, let's take a break here. Yes.